So, welcome to the second lecture of this week, and this lecture we will talk about algebraic algorithms again. We will talk about again inclusion exclusion, give another example, but we will talk about slightly classical formulation. Okay, let me just so, if you recall from the last lecture, the non-classical formulation that we saw is that there are as many odd size subsets and even size subsets sandwiched between two different sets for R subsets of T. And then we derive this formula -1 to the power T minus S R S T is evaluates to 1 when R and T are equal, otherwise it evaluates to 0, because look at the number of sandwich sets of even size and look at the sandwich sets of odd size. So, even size sets are going to contribute 1 to the left hand side sum, and the odd size sets are going to contribute -1, and since they are equal, they are going to cancel out each other, and that is going to be 0. So, this is the classic, but this is not how the formulation of inclusion exclusion generally taught. So, the generally taught is that we are given an universe U, okay, some objects, okay, and now suppose for now you have two sets A and B, right, and A and B are disjoint, then all we can say that A intersection A union B is equal to A plus B, but A and B need not be disjoint. Then all we can say that A union B is at most cardinality of A plus B, because you could have sets say A, B, but the intersection object is counted twice, right, both in A and both in B. So, the basic formula that we could come up with, you have seen this A union, just simple Venn diagram exercise. Okay. But we can also generalize this to 3 sets, right. Right. So, this is A, this is B, and this is C. Okay. Now, we would like to compute the value of A union B union C. So, first, okay. But now notice that there are lots of overcounting going on, right. What is an overcounting going on? Overcounting going on is that these elements are counted for this set, and so on and so forth. So, you try to subtract them out, right. So, this is going to subtract, let us see, this elements. Okay. Now, I also need to subtract out this element. So, this is given by B intersection C, but now also need to subtract out let us say this one. Now, so B intersection C, but I now notice that these elements are subtracted exactly once, because they occur in A and no. So, yeah, so these elements are subtracted exactly once because they are common only between A and C. So, they will only be sorry, this is not into A intersection C. Similarly, these elements are subtracted again how many times? Only once time, because just B and C. So, this is fine. These green elements similarly they are subtracted only one, but look at this common A intersection B intersection C, how many times have they been subtracted, right. So, these elements were counted 3 times. Let us look at A, B and C. So, look at these elements are counted 3 times, each element, one in A, one in B, one in C. Now, this element is subtracted how many times? Let us look at these elements are subtracted when you subtracted A intersection B minus 1 time. These elements are again subtracted when you subtracted B intersection C, so another minus 1 time, and these elements are again subtracted when you did A intersection C. So you have not at all counted them. So now you need to add A once more. Okay. So this is the formula, and now this formula can be generalized to not only 3 sets, but these can be generalized to further, right. And so notice that right hand side contains basically all possible intersections of all possible intersections the sets we have, and the sign depends on the how many sets it intersects. So now generalize this to, suppose you are given over this universe not one set, but you are given sets A1, A2 dot say AN, right, n sets are given, then we can generalize this and we can get this A1 intersection, sorry, A1 union A2 union AN is nothing but summation okay, this is nothing but summation going from phi not equal to, okay, and let me say that n is this index set n, okay. So phi subset of let us say phi not equal to s subset of n minus 1, that is a sign coming in, mod s plus 1 intersection A I in S, right. So basically look at S. So okay, so when will this set, look at S equal to singleton, right, singleton. So then those are going to contribute plus 1. So why did you add plus 1? Because you notice there is an alternation of sign. So one size set contribute, all odd size contributes plus 1, and all even set size contribute minus 1. So if I would have just written cardinality of S for S subset of n, then if it is even set, that contribution would have been positive, but we want that to be negative, so we just added plus 1 to this. Okay. So this is the formula, this is the classical formulation of inclusion exclusion, that if you are interested in counting the union. So this is one formulation, but the more algorithmically useful formulation just follows again from the Venn diagram computation is the following. Okay. Let us say, so let us call this 2 actually. Okay. So this is our second formulation. Let us call the non-classical formulation that is one formulation, first formulation we saw, and there is another formulation which just is achieved by the following. Okay. So equivalently we can say the number of elements, okay, number of elements not in any AI, okay, is what? Okay. So suppose now, so we were counting all the elements that occur in the universe, but suppose I wanted to count u minus this, right. So this is, so I wanted to count the cardinality of universe minus A1 to A, which is nothing but this is same as A1 union A2 union AN complement, and okay, we will prove this in a minute, do not worry. F subset of n minus 1 to the power s I in S AI. Okay. But there is a usual convention notice that I wrote here phi, S was not in phi, but here phi is included. Okay. So, it is an important observation to make. Phi is included in the summation. Okay. Okay. And what is the meaning of this? So, I in phi ai, okay, the convention is this equals the universe, okay, from which the sets are being taken. Okay. So, this is an usual convention. So, in our case this is equal to u. Okay. This is an important observation, this is an important something that we need to remember, right. So, by including this, okay, now let us try to prove the, okay, let us give the proof for, let us call this formulation 3. Okay. And the usual way of showing any such proof is very simple, okay, is that you look at particular element and you see what is its contribution in the left side, what is its contribution in the right side. Okay. So, we considered the contribution of an element A in our universe. And how do we go about proving this? Very simple. So, you look at this index set T. Okay. So, what is this I? And so, this is an I belongs to N, the index set, and what is the property? A belongs to the set AI. So, T is precisely all those sets AI which contains A. Okay. So, what is this T? Basically indexes of those sets that contain the element A. Okay. So, let us ask ourselves, okay, contribution to the left hand side, right. Let us ask ourselves, think for a minute, when are you going to contribute to the left hand side? When? You are going to contribute to the left hand side only when you do not appear in either A1, A2, AN, or in other word, contribution to the left hand side happens when the index set T is empty. Is empty. Okay, fine. Okay. Okay. Now, let us try to determine its contribution to the right hand side. Okay. Let us try to contribute its count, its right. Okay. Let us. So, where does A belongs to? So, A belongs to, okay, I in T, AI, and all its sub intersection, right. Notice, look at where, so what is right hand side? It is all this AI in which like for all index set, their subset, their intersection. So, now I ask myself, I know that A belongs to this index set. So, it means A is in all this T. So, A will appear in every subset of T, because like in the intersection of these elements, these. So, for every S subset of T, I know that A belongs to its intersection, including phi, because phi is nothing but U itself. Okay. 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 This implies A contributes 1 to these terms. Okay. So now the total contribution of A is given by, let's check, right, summation S subset of T minus 1 cardinal T of S, right. This is it, because all we are trying to see is the contribution in A. So A is going to contribute like 1 to all of this, but now you also have the sign. Okay. So this is equal to, right. So now this is equal to minus 1 to the power T. I have just multiplied minus 1 to the power T and plus T, right. So plus T has gone inside, so this will come out. Okay. Now this is exactly the expression 1, and we know this is equal to minus 1 to the power T and when is this term going to contribute? This term is going to contribute when, so how do I am going to apply this? So I am going to apply 1 with R equal to phi. So I could have written this, okay, summation phi S subset of T, right. So if you apply this, then this implies what? Minus 1 to the power T, T equal to phi. This is that notation. So this is equal to minus 1 to the power T, T equal to phi. So if T equal to phi, then this is going to be contribute 1, and yeah. So if T equal to phi, so this is going to contribute 1. So T equal to 0, cardinality of T is 0. So minus 1 to the power 0 is 1. So this is 1. And if T is not equal to phi, this is going to contribute 0. So this is going. So this is, we are going to get T equal to phi. Okay. So basically, to derive this, we used 1 with R equal to phi. So what did we learn? Okay. So we learned that an element A, its contribution to the right hand side is 1 if and only if the index set T is empty. If index set T is non-empty, then A contributes 0 to the right hand side, right. So now we know that we have picked up an element and we have shown that its contribution to the both sides is equal. And if we have shown that its contribution to the both sides are equal, then we have shown the equivalence theory. So look at what does this 3 tells us, that look, if you wanted to talk about some properties A1 to AN, okay, if you wanted to count elements that do not appear in this set, then this particular formula works. I will show to you how actually we use this in algorithm in a context of Hamiltonian cycle and hence for other problem. Okay, but like notice, so like just so yeah. So some remarks are in order. Okay. Look, this and this follows from just De Morgan's law. So this is nothing. This 2 and 3 are exactly the same formulation. If you apply De Morgan law, you will get exactly this. So I am not going to prove why 2 and 3 are equivalent, but 2 and 3 are just straightforward. So basically, what we derived 2 and 3 from 1, right? Using R equal to phi. And let's show now that even opposite direction is fine. Why? So we'll do, so we are going to take, okay. Let T be a finite set. Okay. Let T be a non-empty finite set, okay, it's important that it is a non-empty finite set. Okay. And T equal to 1. And now we are going to consider the family of the identical sets. Consider the family of identical sets. What is this? So, AI equal to say some 1, okay, for all I in T. So, I mean basically I am fixing an index set. So, now I should have started with, so basically what I am saying that you fix up U, some universe, and you come up with the sets A1 to AN, where AN is like each AI is just contains element 1. So, now what we know about these things, that all the union of I equal to 1 to n is 1, intersection AI I equal to 1 to n, and in fact for every subsets of T the intersection and union is 1. So, now if you apply 3, applying 3, what will we get? Applying 3 on these sets, we will get 1 is equal to summation phi. Okay, let us not apply 3, let us apply 2. Okay, let us apply 2. So, applying 2, so what was 2? Remember, the 2 was A1 to AN is this. Okay. So, basically A1 to AN is just 1, and each AI is also going to 1. So, this is basically minus 1 mod s plus 1 and this summation. So, 1 is equal to phi s not equal to phi contained inside this. Okay, great. Now, notice to derive 1, we need that s equal to phi also, right? And but what is s equal to phi? Okay, well, this I can write this minus phi f t minus 1 s plus 1, right, is equal to phi not equal to s subset of t minus 1 mod s plus 1 plus minus 1 to the power 0, which is 1. Okay. We also have 1, right. So, minus 1 to the power 1, this is, so this quantity and minus 1. Okay. So, this is this quantity minus 1. So, what do we get? So, this quantity equal to minus 1. So, what are we going to get is this is equal to, but this we know is equal to 1. So, 1 minus 1 which is equal to 0, right. So, we applying to we got this, and now to derive 1 we started, this is what we were interested in, right. Now, you might ask, but this is not what we were interested in. We were interested in, let us look at, so this is what we get. So, but we were interested in minus 1 t minus s, this is the expression we were interested in. Okay. And now, I show you that this and this expression are equivalent. Prove it. Okay. So, you can show that the parity will not change. Parity of minus 1 t minus s is same as or for each, this is exactly same. So, once you have done this, okay. Okay. So, now that we have shown this classical formulation of inclusion exclusion, that if you are interested in counting intersections of elements or counting if you are interested in counting union of elements or complement of it, then this is the way to derive the formula. Okay. How do we use algorithmically? So, to use algorithmically, I am going to explain to you via an example, and we are going to derive an algorithm for Hamiltonian path, or say Hamiltonian path or Hamiltonian cycle. Okay. So, let us say we are interested in Hamiltonian path. Okay. So, what is a Hamiltonian path? Ham path in a graph is a path that visits every vertex. Okay. So, that visits every vertex, that is it, that is important point. That so, it is basically a path that visits every vertex. Okay. It is well known that it is well known a classical NP hard problem, and so what we are going to give now is 2 to the power n. N is number of vertices. Okay. Yeah, n is the number of vertices. Okay. So, we are okay, and now okay, and let us say for ease of notation, okay, let us say that all path start in node say V1 equal to 1. This is just for use of notation. Okay. And now, what I am going to decide, so the way you are going to work out these things is, what is my universe? So, my universe is going to be something which will be slightly easier object to count. Okay. Now, what I am going to do, okay. So, now suppose we are given a graph G on n nodes, say, okay, given a graph G on n nodes, say n, let A of x, okay, what is A of x? It denotes the walk of length n that starts in first vertex, the pre-specified vertex, and avoids any vertex in x. Okay. So, for example, okay. Now, notice, okay, if I say give me a walk of length n, say n is even, okay, between a vertex 1, okay. Now, and that should avoid this vertex, this vertex, this vertex, this vertex, then this is nothing but I come, I go, I come and I go, I come and go, right. Okay. So, this is, so in walk a vertex can be repeated, edges can be repeated, okay, but it is a path when every vertex appear at most 1. So, what I am saying that I want a walk of length n, so you start from a vertex which starts at 1 and avoids any vertex in x. So, I could have maybe gone like this, but that does not avoid these set of vertices, okay, that does not avoid these set of vertices. So when I say I want to have a walk of length n that avoids, means I start from vertex 1, I take n, like I just pick up some n edges but in a continuous fashion, like in the, what I mean. So if I pick up, I start from vertex, I go to some other vertex, and then at that point of time, it's not that I have to avoid this edge. I could pick up any edge starting from this vertex and move to another vertex, then pick up that vertex, avoid any. So but if I have to avoid any vertex in X, it's just that I have to make sure that at any point of time I do not pick up a vertex in X. I only take those edges that does not contain an endpoints of X. So this is how we will denote. So now what is our universe is going to be? So universe is going to be all walks of my length n, all walks of length n starting at 1. So this is my universe. Okay, this is my universe. Now notice, what is A of phi? What is A of phi? A of phi is, what is this? A of phi is set of what denotes the, denotes the number of walks. Okay. So what is A of I? Set of, okay, rather set, not set of walks, number of walks of length n that avoids phi. So now what is A of phi counts? This is nothing but precisely number of Ham paths, because if you are a walk of length n and okay. So number of walks of length n that avoids phi, right? It means this walk contains every other vertex, right? And so basically now it's a walk which contains every other vertex, and since it's of length n, every vertex appears at most one time. So this is nothing, this walk is nothing but a classical path. So no edge will be repeated, no vertex is repeated. So A phi is a number of walks of length n that avoids phi. Now we need to set up some sets over U. So what do we set up the sets? So we set up some sets. What is AI? Okay, AI is basically, it denotes the walk that avoids the vertex I, right? That's it. Then you ask yourself, what is A of phi then in terms of this? Well, look at, let's ask ourselves first, what is union AI? A1, union A2. So basically A1 union A2 are those walks. So what is A1? It is those set of walks that avoids A1. It is A2, which is those set of walks that avoids element 2, so on and so forth. Okay. So if I take the union, okay, so look at A1 to AN. Okay, what does A1 to AN consist of? Look, so A1 to AN, this consists of all works that avoids at least one I. So, what is a complement of A1 union A2 union AN bar is basically what will be there in those. This is basically is going to be Hamiltonian path, right. So, this is, so if I take the cardinality of this is exactly what A of phi is. Okay. Now, that we have set up everything, now let us apply our formula, right, the third formula that we derived. Okay. From 3, what will we get? Get is the following, that A of phi is x subset of 1 minus 1 to the power x A of x. That is it, right. This is the third formula that we derived, right. This is A phi minus 1 to the power say AI I in S. So, which is basically what is you, for us you avoid every element in S. So, which is nothing but directly cardinality of A of x, A of S. Okay. So, if we had some way, right, if we had some way to compute A of x, we will be very good. So, how will we do? For every x subset of n, we can, A of x can be computed in polynomial time. We will see in a minute, very simple dynamic programming, okay, using dynamic programming over over the lengths, okay, and endpoints, not over subsets, okay, that is important point, not over subsets. Okay. So, let us see what I mean by this. Okay. So, for every t in Vg, okay, and the length can be 1 to n, okay, okay, k could be 1 to n. Okay. I am going to say what is this A k x t, okay, is number of walks of the form what 1, you start in 1 V2 dot 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 Vk, where Vk, so you start in 1, you end in t, this is what it tells us, and you still avoids the vertices in x. So, none of these vertices appear in, so, and so that is basically saying that Vi is not in x. And how do we do this? Okay, so we can, so this dp we can set up. So, let us ask yourself A1 x v, what is this? This is exactly evaluates to 1 if v is equal to 1 and 0 otherwise. Okay. Okay. So, basically, yeah, that is it. And what is, so suppose you have computed a k x t, so you can compute a k plus 1 x t as summation over v in v a k. So, it is like you ask yourself, right. So, I start from 1, I reach some vertex v, right, and then I take a, oh, then I take a edge, then I take an edge starting at V. So, how is a walk of length k plus 1? You start from 1 to some other vertex V with length k. V could very well be, yeah, and then you take an one edge to T. So, this is nothing but V in V, and so you reached V, and then what is the property? V comma T should be in the edge. So, the property P that hold is that V T belong to my graph, and that is it. Okay. So, this is it. This is the way we can compute k plus 1 length. So, you first compute a length like A1 xv for every vertex, then A2 xv for every vertex, then A3 xv for every vertex, so on and so forth. And this is how you can count all the walks starting from 1 to length. There is also you can do using what you call adjacency matrix, but we will not talk about. So, the total time to compute A x is same as T in V A x T. So, you can very well check that this is all polynomial time. Yeah. So, you can compute A x in polynomial time. I am not going to spend more time on this, but notice it is a very good, right. Now, so now you compute A of x, keep it in, and then you go over all x subset of n, A of x, like you go over all x subset of n, you compute A of x, and then you do minus 1 to the power x. So, you can evaluate this sum or the expression in actually 2 power n time into poly time and actually polynomial space. So, we can compute the number of Ham paths in time 2 power n, n to the power big O of 1, and space n to the power big O of 1. So, in poly space in 2 power n time we can compute number of Hamiltonian paths. Okay. So, this was another example of inclusion-exclusion based algorithm. There are several more, but I will leave it to that, and we will do some other tools or techniques in the next lecture. Thank you.